Beneath Greenland's ice lies a hidden network built in silence, protected by forgotten treaties and buried under decades of snow. Satellites now see straight through it. Seismographs have recorded signals that should not exist. Classified blueprints, abandoned reactors, and unexplained vibrations are converging into one unanswered question. Who built this? Why was it hidden? And what is still buried below? What scientists just detected is forcing governments to reopen files meant to stay closed forever. Measured traces across frozen ground. In November 2024, NASA released a radar image showing linear patterns beneath the surface of the Greenland ice sheet. The data came from an airborne survey using UAVSR, a synthetic aperture radar system operated by the Jet Propulsion Laboratory. The aircraft was part of a routine campaign to measure ice deformation and internal layering. Chad Green and Alex Gardner were among the researchers analyzing the results. During processing, the radar returns revealed intersecting lines that contrasted with the surrounding natural ice layers. The geometry corresponded with archived maps of Camp Century, a U.S. Army installation constructed beneath the ice in 1960. The radar system does not photograph physical structures. It transmits microwave pulses that penetrate snow and ice and reflect off boundaries where material properties change. Buried voids, metal supports, and compacted construction zones produce stronger reflections than surrounding fern. When visualized, these reflections appear as continuous bands and sharp angles. In the 2024 dataset, the arrangement formed a recognizable grid. NASA's Earth Observatory published the image on the 25th of November 2024, describing it as a technical demonstration of subsurface mapping capability. Camp Century is located in northwestern Greenland at an elevation of approximately 2,000 meters above sea level. It lies about 150 miles from Thule Air Base, now known as Pituffik Space Base. Construction began in 1959 under the direction of the U.S. Army Corps of Engineers. Workers cut long trenches into compacted snow using trenching machines and explosives. Corrugated steel arches were installed to form roofs. Snow was pushed back over the arches and allowed to harden. Inside the covered trenches, prefabricated wooden buildings were assembled. The main corridor ran several hundred meters and connected living quarters, laboratories, storage rooms, and mechanical spaces. Personnel referred to it informally as Main Street. Side trenches branched from the central passage at regular intervals. Engineering reports from the early 1960s describe approximately 21 primary trenches with a combined length exceeding 3 kilometers. The layout followed practical spacing for ventilation and access rather than strict symmetry. Nonetheless, from above, the system resembled a rectangular network. Officially, Camp Century functioned as a polar research station. Scientists conducted snow accumulation studies, meteorological observations, and early deep ice coring. The camp also served as a test site for subsurface construction in polar environments. At the same time, internal military planning documents connected the facility to Project Iceworm. This classified program explored whether nuclear missiles could be deployed in mobile launchers beneath the ice sheet. Declassified material from the early 1990s describes a theoretical network extending thousands of kilometers. The concept relied on continuous excavation and relocation to counter ice movement. Ice deformation became apparent within the first year of operation. Measurements taken in 1961 showed that trench walls were narrowing by several centimeters per month in some areas. Ceilings sagged as overlying snow compressed. Maintenance crews routinely cut and scraped ice to keep corridors open. Technical logs note repeated adjustments to doors, piping, and electrical conduits. Engineers concluded that maintaining a large underground network would require constant reconstruction. Power generation was provided by the PM-2A nuclear reactor installed in 1960 and activated in 1961. The reactor supplied electricity and heat to the camp for several years. Diesel generators served as backup. Operational records describe challenges related to ventilation, radiation monitoring, and heat management in enclosed ice spaces. In 1964, the reactor was dismantled and removed. Some contaminated water and auxiliary materials remained buried at the site. By 1966, Camp Century was decommissioned. Personnel and major equipment were withdrawn. Buildings, pipes, fuel residues, wastewater, and other materials were left in place. The prevailing assumption was that continued snowfall would bury the site deeper over time. Accumulation rates in the region averaged more than 0.5 meter of snow per year. Planners expected that the installation would remain isolated from surface processes indefinitely. Scientific assessments in later decades revisited this assumption. Satellite measurements and field studies showed that surface melting in Greenland was increasing. In 2016, a study led by William Colgan at the Geological Survey of Denmark and Greenland evaluated the long-term stability of buried waste at Camp Century. The analysis suggested that warming could eventually cause meltwater to percolate downward, potentially mobilizing contaminants. The camp became a case study in how historical infrastructure interacts with changing ice dynamics. The 2024 radar image placed these concerns in a new observational context. It demonstrated that the structural layout of Camp Century remains distinct within the ice. The tunnels have not collapsed into indistinguishable layers. Instead, their outlines persist as zones of altered density and composition. NASA's accompanying explanation focused on instrumentation. The agency emphasized that UAV-SAR can map internal ice features over large areas without drilling or excavation. In September 2023, Greenland became the focus of another instrument-based observation. On the 16th of September 2023, seismic stations detected an unusual, narrow-band signal. The dominant period was approximately 92 seconds. Unlike typical earthquakes, the vibration did not decay within minutes. It continued for 9 days. The signal appeared on records from Europe, North America, and Asia. Initial automated classifications did not match known seismic patterns. Stephen Hicks at University College London and other researchers began comparing datasets. The waveform showed a stable frequency near 10.8 MHz. It lacked the broadband energy associated with tectonic ruptures. Satellite imagery from the same period revealed changes in Dixon Fjord in East Greenland. A large section of mountain slope had collapsed into the water. The landslide consisted of rock, ice, and debris. Field investigations and remote sensing confirmed that the landslide generated a major tsunami. Run-up marks on fjord walls indicated wave heights exceeding 100 meters in some locations. The fjord's narrow shape trapped the water. Instead of dispersing, the wave reflected repeatedly between the steep sides. This produced a standing oscillation, known as a seiche. Each oscillation transferred energy into surrounding rock. The repeated impacts generated the long-lasting seismic signal. A paper published in Science in December 2023 modeled the interaction between water motion and bedrock. The authors showed that the fjord's length and depth matched the observed oscillation period. Data from Sentinel satellites and commercial imagery were used to estimate the landslide volume. Researchers from Denmark, Greenland, the United States, and the United Kingdom contributed to the analysis. The LRO research station, located within the fjord system, reported structural damage consistent with a large wave. Equipment and supplies were displaced. Debris lines marked the extent of flooding. These observations provided on-site confirmation of satellite and seismic data. Maritime activity in the region is limited, but earlier in September 2023, the cruise vessel Ocean Explorer required assistance after grounding in a nearby fjord. The incident highlighted the logistical constraints of operating in remote Arctic waters. Both the buried installation and the 9-day seismic signal became widely recognized through measurement systems. Seismometers converted water motion into frequency plots. In each case, the primary evidence consisted of numerical records, timestamps, and spatial coordinates. Researchers validated the observations by comparing independent datasets. Greenland's ice sheet covers approximately 1.7 million square kilometers. Beneath it lie geological formations, abandoned facilities, and sediment layers. Along its coasts, steep fjords amplify the effects of slope failures and waves. Continuous monitoring networks record changes in these environments. The data accumulate in archives long before they are discussed publicly. The radar detection in 2024 and the seismic signal in 2023 represent separate events. One relates to Cold War engineering preserved in ice. The other reflects a geophysical response to a modern landslide. Both were identified through instruments designed for broader environmental monitoring. Their documentation consists of dated files, calibrated measurements, and peer-reviewed analyses. Blueprints in rooms without windows. Stacks of paper filled a narrow storage room in the Pentagon's engineering wing during the late 1950s. The folders were labeled with neutral terms such as polar construction, cold regions testing, and subsurface facilities. Inside were drawings, stress calculations, supply estimates, and field reports prepared for work in northwestern Greenland. These documents formed the administrative foundation for Camp Century. They described ice as a material to be measured, cut, reinforced, and maintained, using methods adapted from mining and snow science rather than conventional building practices. The earliest design drafts treated the Greenland ice sheet as a layered structure. Engineers divided it into zones of surface snow, compacted fern, and deeper glacial ice. Each layer was assigned density values and compression rates based on field studies from Alaska and Antarctica. Reports from the U.S. Army Cold Regions Research and Engineering Laboratory in Hanover, New Hampshire, were frequently cited. These studies provided formulas for predicting how quickly tunnels would narrow under load. Planners relied on these equations when selecting trench depth and spacing. By 1958, preliminary layouts had been standardized. The main corridor was designed to run east to west, perpendicular to prevailing winds, to reduce snow drifting at entrances. Secondary corridors were spaced to balance structural stability and accessibility. Drawings specified exact distances between arches, ventilation shafts, and electrical conduits. Margins of safety were built into most measurements. In practice, many of these margins proved smaller than anticipated. Transport planning occupied much of the early correspondence. No permanent road linked Thule Air Base to the construction site. Supplies were moved using tracked vehicles and sled convoys over ice and snow. Fuel consumption estimates were revised repeatedly after early test runs showed higher than expected losses in deep snow. One internal memo from 1959 noted that transporting a single reactor component required more than 20 vehicles operating in sequence. Excavation schedules were coordinated with seasonal temperature cycles. Snow and fern behaved differently at -40 degrees Celsius than at -10. Engineers preferred colder conditions, which reduced wall collapse during trench cutting. However, machinery performance declined in extreme cold. Balancing these factors became part of routine planning. Weekly progress charts tracked excavation depth, wall stability, and equipment downtime. Once trenches were opened, installation followed strict sequences. Steel arches were placed first, aligned using temporary wooden frames. Bolts were tightened according to torque tables included in assembly manuals. Insulation panels were fitted along the interior surfaces. Electrical wiring and water pipes were installed before snow was replaced over the roof. Thermal management appeared early as a major design concern. Heating systems were required to maintain indoor temperatures suitable for personnel and equipment. At the same time, excess heat accelerated ice deformation. Calculations attempted to predict heat flow through walls and ceiling. Engineers modeled how much energy would be absorbed by surrounding ice and how quickly it would dissipate. Field measurements later showed that localized warming was difficult to control. Ventilation systems were designed to regulate humidity and remove exhaust gases. Blueprints specified fan capacities and duct diameters. Pressure differentials were calculated to prevent condensation buildup. Despite these precautions, maintenance logs from the early 1960s record frequent ice accumulation on ducts and vents. Crews were assigned regular scraping duties to keep airflow within planned limits. Project Iceworm planning expanded these technical issues to a larger scale. Feasibility studies drafted between 1959 and 1962 explored how hundreds of kilometers of tunnels might be arranged. Proposed layouts resembled branching grids, with main arteries and secondary spurs. Mathematical appendices included simulations of long-term creep based on assumed ice temperatures and impurity levels. Some models predicted acceptable deformation rates. Others suggested rapid closure. Survey data from Camp Century became critical for evaluating these projections. Measurement teams installed reference points along walls and ceilings. Distances between markers were recorded monthly. These datasets were transmitted to analysis groups in the United States. Comparisons between predicted and observed deformation revealed consistent underestimation of closure rates. Revised models incorporated higher creep coefficients. Water management presented additional complications. Meltwater formed from heat sources and human activity. Drainage channels were carved into floors and connected to collection pits. Pumps transferred water to disposal areas. As tunnels narrowed, gradients shifted, causing water to pool in unexpected locations. Maintenance crews modified channels repeatedly. Updated drainage maps were circulated every few months. Electrical and communication networks were also affected by ice movement. Cables stretched and insulation cracked. Junction boxes shifted out of alignment. Engineering reports document multiple redesigns of cable routing to accommodate deformation. Flexible couplings were introduced after rigid systems failed. These adjustments increased material requirements and labor costs. Financial planning reflected these realities. Budgets initially assumed moderate maintenance expenditures. By 1962, Revised estimates showed rising personnel and equipment demands. Cost-benefit analyses compared continued operation with potential relocation. Although Camp Century remained active, expansion plans were gradually curtailed. Iceworm proposals were scaled back in successive drafts. Closure planning began earlier than publicly acknowledged. By 1965, internal files included decommissioning outlines. These listed procedures for equipment removal, waste disposal, and structural mapping. Engineers prepared final surveys showing tunnel positions and dimensions. The last measurements confirmed substantial reductions in cross-sectional area across much of the network. After abandonment in 1966, the engineering records entered long-term storage. For decades, they were consulted mainly by historians and military analysts. Interest increased in the 2000s as climate studies raised questions about buried materials. Digitization projects converted handwritten tables and faded drawings into searchable databases. Researchers used these files to reconstruct waste locations and structural depth. The technical culture behind Camp Century emphasized documentation. Every modification generated new diagrams. Every anomaly produced a report. Even routine maintenance was logged with timestamps and measurements. This practice created a detailed archive of interaction between human construction and glacial movement. Through these documents, the buried grid can be followed from initial sketches to its present form beneath accumulated snow. Machines that listen, without sound. Long before any pattern appears on a public image or in a scientific journal, it passes through layers of equipment housed in quiet buildings. In Greenland's case, much of that process begins inside metal racks filled with circuit boards, cooling fans, and storage drives. These systems operate in aircraft, satellites, and remote stations, collecting continuous streams of numerical signals. They do not record scenery, they register variations in energy, time delays, and frequency shifts that must later be translated into spatial information. The UAVR system used in Greenland operates from modified research aircraft. It transmits microwave pulses toward the surface and records the returning echoes. Each pulse lasts only microseconds. The time between transmission and return determines distance. Differences in phase and amplitude reveal changes in material density and structure. During flights over the ice sheet, millions of such pulses are emitted every second. Raw data are stored on board before being transferred to processing centers in California. Once downloaded, the radar signals are corrected for aircraft motion, atmospheric interference, and instrument drift. Engineers apply algorithms that align successive pulses and remove background noise. The result is an interferometric dataset that shows how signals interact with subsurface layers. In polar regions, dry snow and ice allow deeper penetration than in temperate environments. This property makes Greenland suitable for internal mapping using radar systems originally designed for surface studies. Processing pipelines convert these datasets into layered images. Each layer represents a different depth interval. Bright lines indicate strong reflectors. Diffuse areas suggest uniform material. In the 2024 Camp Century dataset, analysts observed linear reflections that remained stable across multiple passes. Cross-referencing with historical maps confirmed their alignment with known tunnel positions. Radar features are routinely compared with ground records and earlier surveys before interpretation. Satellite-based instruments perform similar functions at larger scales. Missions such as Sentinel use synthetic aperture radar to monitor surface displacement and ice velocity. Although these satellites operate at higher altitudes, their data contribute indirectly to subsurface interpretation. Variations in surface flow often correspond to internal structures or basal features. Scientists combine airborne and orbital datasets to construct three-dimensional models of ice behavior. Data management is central to this process. A single UAVR campaign can generate several terabytes of information. These files are archived in distributed storage systems. Metadata include timestamps, flight coordinates, antenna orientation, and calibration constants. Without this contextual information, the numerical records lose analytical value. Documentation protocols require that every dataset be accompanied by technical summaries describing instrument settings and environmental conditions. Seismic monitoring follows parallel principles. Global networks, such as the International Federation of Digital Seismograph Networks, maintain stations that continuously record ground motion. Each station uses sensitive sensors capable of detecting displacements smaller than a micron. Signals are digitized and transmitted to regional data centers. Automated systems classify events based on waveform characteristics before human review begins. The September 2023 Greenland signal entered this system as an anomaly. Its narrow frequency band did not match earthquake templates. Software flagged it for manual inspection. Analysts examined raw traces from multiple stations and compared arrival times and amplitudes to determine source location. Triangulation placed the origin in East Greenland. The persistence of the signal required adjustments to filtering routines, normally optimized for short-duration events. Frequency analysis played a central role. Researchers applied Fourier transforms to isolate dominant periods. The consistent 92-second cycle stood out. This periodicity suggested a mechanical oscillator rather than tectonic rupture. Similar patterns had been observed in lakes and reservoirs affected by seiches, but rarely at continental scale. The Greenland case required integration of hydrodynamic modeling with seismic interpretation. To support these models, scientists needed accurate fjord geometry. Bathymetric surveys provided depth profiles. Some were derived from ship-based sonar, collected decades earlier. Others came from modern multi-beam systems. These datasets were merged and interpolated to create digital elevation models of the fjord basin. The resulting grids were used to simulate wave behavior under different landslide scenarios. Satellite imagery supplied additional constraints. Optical images from Landsat and Sentinel, two documented surface changes after the landslide. Radar satellites detected slope deformation preceding collapse. Analysts compared images from different dates to estimate the volume of displaced material. These estimates fed into tsunami generation models, which predicted oscillation periods consistent with seismic observations. Verification requires redundancy. No single instrument is treated as definitive. Radar interpretations are checked against ice cores and GPS measurements. Seismic reconstructions are tested using independent station arrays. Discrepancies trigger reanalysis. In the Greenland case, teams from Denmark, the United States, and the United Kingdom shared datasets and processing scripts to confirm results. Noise reduction remains a persistent challenge. Radar signals are affected by surface roughness, meltwater layers, and atmospheric moisture. Seismic sensors pick up traffic, machinery, and storms. Analysts apply filters to remove these components. Excessive filtering, however, can eliminate meaningful signals. Balancing clarity and completeness requires iterative testing. Calibration procedures aim to maintain consistency across time. Instruments are periodically tested using reference sources. Radar antennas are measured for beam stability. Seismic sensors are checked using controlled vibrations. Calibration constants are updated and logged so that changes in data reflect environmental variation rather than equipment drift. Human oversight remains essential. Automated systems identify candidate features, but specialists review them. Radar interpreters examine cross-sections manually. Seismologists inspect waveforms visually. Training emphasizes recognition of artifacts produced by processing errors, such as misaligned flight paths or corrupted timestamps. The infrastructure supporting these activities extends beyond Greenland. Data centers in California, Germany, and Denmark store and distribute records. High-speed networks enable near real-time access. Standardized formats allow researchers to exchange information efficiently. Collaborative platforms host shared analysis notebooks and model outputs. Over time, accumulated datasets form long-term records. Ice thickness maps from the 1960s can be compared with modern surveys. Seismic catalogs span more than a century. These archives provide context for interpreting new observations. When the 2023 signal appeared, analysts consulted historical records to rule out similar past events. Technological evolution alters observational capacity. Early radar systems produced coarse profiles. Modern instruments resolve features at meter-scale resolution. Seismographs once recorded on paper drums. Today, they stream digital data continuously. These advances increase sensitivity, but also expand data volume, requiring more complex management. Despite this complexity, the underlying principle remains simple. Instruments convert physical processes into numerical form. Interpretation consists of linking those numbers back to material structures and movements. In Greenland, this translation connects buried corridors to radar reflections and oscillating fjord water to frequency spectra. The machines listening beneath Greenland's ice do not distinguish between historical remnants and natural processes. They record variations in reflected energy and ground motion. Meaning is assigned later through comparison, calibration, and verification, forming the technical foundation of modern observation. inventories written for conditions that no longer exist. Deep inside military archives and environmental assessment reports are tables listing objects that were never intended to be revisited. They describe drums, pipes, tanks, cables, solvents, and structural debris, recorded at the time of abandonment and filed as closed records. At Camp Century, these inventories were compiled in the mid-1960s, when the site was dismantled and vacated. Engineers and administrators documented what was removed and what was left behind. Their assessments reflected prevailing assumptions about ice stability and long-term burial. Closure documentation from 1966 indicates that most transportable equipment was shipped back to the United States. Vehicles, generators, and laboratory instruments were removed. The nuclear reactor had already been dismantled 2 years earlier. What remained consisted largely of fixed infrastructure and waste products. These included steel arches, wooden framing, electrical wiring, insulation panels, fuel residues, wastewater, and chemical solvents used for maintenance and cleaning. Diesel fuel was stored in underground tanks and pipelines. Records indicate that several tens of thousands of liters were present at various stages of operation. Not all fuel was drained during closure. Residual amounts remained in lines and storage vessels. Over time, some of these containers corroded. Engineers at the time considered this inconsequential, given expectations of permanent entombment. Wastewater management at Camp Century relied on shallow disposal pits and drainage systems. Human waste, grey water, and laboratory effluent were directed into designated areas beneath the ice. These zones were mapped in internal files, but not isolated with impermeable barriers. The design assumed that frozen conditions would immobilize contaminants. Chemical composition analyses were limited, reflecting environmental standards of the period. Polychlorinated biphenyls, or PCBs, were present in electrical equipment and insulating materials. These compounds were widely used in the mid-20th century for their heat resistance. Later research classified them as persistent organic pollutants. Closure inventories from Camp Century list transformer oils and electrical components containing PCBs. No removal program was implemented before abandonment. Low-level radioactive material associated with reactor operations remained embedded in cooling systems and surrounding snow. While the reactor core and major components were removed, auxiliary piping and contaminated water were left behind. Technical summaries from 1964 and 1965 describe this residue as minimal and stable. Monitoring plans did not extend beyond initial decommissioning. Structural debris accumulated as tunnels narrowed. Buckled supports, collapsed panels, and discarded equipment were often buried in place rather than transported out. Maintenance crews pushed damaged materials into unused sections. Over time, these areas were sealed by snowdrift and ice movement. Closure maps show several such zones distributed across the tunnel network. For decades after abandonment, these records received little attention. The site was inaccessible, and no direct inspection occurred. In the 1990s, declassification of iceworm-related files brought renewed interest from historians. Environmental implications were not yet central to the discussion. Focus remained on Cold War strategy and engineering feasibility. This changed in the early 2000s, when climate research began documenting accelerating surface melt in Greenland. Satellite observations showed expanding melt zones and longer melt seasons. Hydrological studies demonstrated that surface water could penetrate deep into the ice through moulins and fractures. These findings raised questions about the long-term isolation of buried materials. In 2014, researchers from the Geological Survey of Denmark and Greenland initiated a comprehensive review of Camp Century's environmental legacy. They assembled historical inventories, construction diagrams, and waste disposal records. These documents were digitized and cross-referenced. Locations of fuel tanks, waste pits, and reactor-related structures were reconstructed using archived maps. A 2016 study led by William Colgan synthesized this information with climate projections. The analysis modeled how warming scenarios could alter accumulation and melt patterns. Results indicated that by the late 21st century, meltwater could intersect the buried site. Under certain scenarios, seasonal melting could reach depths sufficient to mobilize contaminants. The study did not predict immediate exposure. It emphasized gradual processes. Meltwater percolation, refreezing, and refreezing cycles would transport dissolved substances slowly. Over decades, this could lead to redistribution of pollutants within the ice. Eventually, some materials might reach the surface or enter meltwater streams flowing toward the coast. Follow-up assessments refined these projections. Updated climate models incorporated regional variations in snowfall and temperature. Ground-penetrating radar surveys helped determine current burial depth. Measurements suggested that Camp Century lay approximately 30 to 35 meters below the surface in the early 2020s. Accumulation continued to exceed melt at that location, but trends showed narrowing margins. Sampling campaigns were limited. No drilling directly into waste zones was conducted. Researchers relied on indirect evidence and historical records. Ethical and logistical constraints discouraged intrusive investigation. Disturbing the site could accelerate contamination pathways. As a result, most evaluations remained theoretical. Parallel concerns existed at other Arctic installations. Abandoned radar stations, weather outposts, and fuel depots across Greenland and northern Canada contained similar materials. International agreements addressed some cleanup efforts, but remote inland sites were rarely prioritized. Camp Century stood out because of its scale and detailed documentation. Political responsibility remained ambiguous. The facility had been operated by the United States on Danish territory under Cold War agreements. Environmental governance frameworks developed decades later. Diplomatic discussions in the 2010s acknowledged shared interests in monitoring the site. No binding remediation plan was adopted. Internal correspondence from Danish ministries shows cautious language. Officials referred to long-term observation and future assessment. Budget estimates for full removal ran into hundreds of millions of dollars. Technical feasibility was uncertain. Excavating deeply buried waste would require large-scale ice removal and long-term field operations. Remote sensing offered limited insight into material condition. Radar could reveal structural outlines, but not chemical states. Satellite imagery tracked surface melt, but not subsurface flow paths. Numerical models filled the gap, using assumptions based on laboratory experiments and small-scale field studies. The legacy materials at Camp Century thus exist in a state of deferred management. They are documented, mapped, and modeled, but not actively controlled. Their stability depends on climatic conditions that were not anticipated during construction. Original planners assumed a static environment. Contemporary assessments emphasize variability. The 2023 Dixon Fjord event added context to these discussions. The landslide demonstrated how rapidly Arctic systems can reorganize. Large volumes of material were displaced in a single event, altering local hydrology. Although unrelated to Camp Century, the episode reinforced awareness of environmental thresholds. Archival records from the 1960s described disposal practices in neutral terms. Waste zones were labeled inactive. Fuel residues were classified as immobilized. These terms reflected the scientific understanding of the time. Modern terminology emphasizes mobility, pathways, and risk gradients. Efforts to maintain updated inventories continue. Researchers periodically revise location estimates using new radar data. Climate models are recalibrated as observational records lengthen. These updates are published in technical reports rather than policy statements. Their purpose is to maintain situational awareness. The material legacy beneath the ice is therefore defined by documentation rather than direct observation. Lists, maps, and projections form the primary basis for understanding. Each revision depends on both historical accuracy and modern measurement. What remains at Camp Century is not only physical matter, it is also a record of how environmental assumptions shape engineering decisions. Materials were placed where they were because they were expected never to move. Changing conditions challenge that expectation without immediately overturning it. The buried inventories persist as reference points in environmental research. They link Cold War infrastructure to present-day climate analysis. Their relevance grows not through dramatic change, but through gradual adjustment of models and records as new data become available. Clauses embedded in distant agreements. In a climate-controlled reading room within Denmark's National Archives, a bound volume titled Defense of Greenland, 1951 rests among thousands of similar records. Its pages are thin and closely printed, reflecting administrative practices of the early Cold War. The document contains the formal agreement, signed in April 1951, by representatives of Denmark and the United States. It established the legal framework for American military activity in Greenland. The text makes no reference to underground bases, nuclear reactors, or waste disposal. Instead, it outlines access rights, jurisdictional authority, and operational privileges in broad terms that later shaped every major installation. The 1951 agreement granted the United States extensive freedom to construct and operate defense facilities. Denmark retained formal sovereignty, while practical control over designated areas rested largely with US forces. Environmental protection was not mentioned. At the time, international environmental law was limited, and Arctic regions were regarded primarily as strategic frontiers and scientific laboratories. Supplementary arrangements followed during the late 1950s. Technical protocols adopted in 1957 and 1958 addressed airfield expansion, radar networks, and inland supply routes. Camp Century was planned and constructed within this administrative framework. Internal correspondence indicates that Danish officials were informed of the facility's general research purpose. Detailed references to Project Iceworm remained restricted within American military channels and were not shared through formal diplomatic documents. Jurisdiction within U.S. operated zones was divided. American military law governed U.S. personnel, while Danish civil law retained theoretical authority over Greenlandic territory. In practice, enforcement depended on cooperation rather than litigation. Joint committees handled disputes involving labor, customs, and infrastructure. This system functioned effectively for routine matters and reduced the need for formal legal intervention. Environmental oversight mechanisms were minimal. Waste disposal and infrastructure management followed U.S. military standards of the period. These standards prioritized containment through burial and isolation. Danish agencies did not conduct independent inspections of subsurface facilities. Technical responsibility rested almost entirely with American engineering units, which reported internally rather than through bilateral review. When Camp Century was closed in 1966, no specific bilateral agreement addressed environmental remediation. Decommissioning followed U.S. Army procedures. Danish ministries received summary reports stating that the site had been stabilized and secured. These reports focused on physical safety and restricted access. Detailed inventories of remaining materials were not included in diplomatic exchanges. Legal perspectives began to change in the 1970s. International concern about pollution increased following major industrial accidents and the emergence of multilateral environmental treaties. Denmark ratified several conventions regulating hazardous substances and waste transport. These frameworks focused on active industries and shipping routes. Abandoned military sites in remote regions received little attention. Greenland's political status evolved in parallel. The introduction of Home Rule in 1979 expanded local authority over internal affairs, including environmental regulation. Defense policy, however, remained under Danish jurisdiction. Agreements with the United States continued to be negotiated at the state level. Camp Century, already inactive, remained outside most administrative reforms. During the 1990s, declassification of Cold War records renewed interest in Project Iceworm. Danish parliamentary committees reviewed historical cooperation with the United States. Their reports acknowledged limited knowledge of certain activities during earlier decades. Environmental implications were noted briefly but not examined systematically. The emphasis remained on historical transparency rather than legal accountability. A more detailed reassessment followed advances in climate research. By the early 2010s, studies suggested that warming trends could affect buried infrastructure. In 2014, Danish and Greenlandic authorities requested technical evaluations of former U.S. sites. These requests were framed as scientific assessments. Correspondence emphasized data sharing and joint interpretation rather than liability. The 2016 study on Camp Century's long-term stability prompted formal diplomatic discussions. Officials from Denmark, Greenland, and the United States exchanged technical memoranda. The documents avoided accusatory language. They emphasized uncertainty, model limitations, and the need for continued monitoring. Responsibility was described using terms such as shared and context-dependent. No binding commitments were proposed. International law provided limited guidance. The 1951 agreement predated modern environmental liability regimes. Later treaties generally excluded activities conducted before their adoption. Legal scholars noted that retroactive application would involve complex jurisdictional questions. Greenland's status within the Kingdom of Denmark added further ambiguity. Economic considerations shaped negotiations. Comprehensive remediation would require large-scale excavation and transport in extreme conditions. Engineering assessments suggested costs reaching hundreds of millions of dollars. No agreement specified funding responsibility. As a result, Policy discussions prioritized observation and modeling over intervention. Institutional memory affected interpretation. Many officials involved in early agreements had retired. Archival records were incomplete. Some technical annexes remained classified or had been lost. Working groups were formed to reconstruct legal intent from fragmented documentation. Their findings were provisional rather than definitive. Comparable issues appeared at other former US installations in Greenland, including distant early warning radar stations and meteorological outposts. Cleanup efforts focused mainly on accessible coastal sites. Inland facilities remained largely untouched due to logistical barriers. Camp Century remained distinctive because of its nuclear history and extensive documentation. Public communication remained cautious. Government statements referred to ongoing dialogue and scientific cooperation. Press releases avoided timelines. Parliamentary debates in Denmark during the late 2010s reflected concern but emphasized diplomacy. Greenlandic representatives highlighted environmental stewardship and long-term monitoring. The United States maintained that operations complied with contemporary standards. Officials cited the absence of immediate contamination evidence and expressed willingness to support research. Formal acceptance of liability was not issued. Cooperation was framed as voluntary and collaborative. Gradually, joint monitoring mechanisms emerged. Data-sharing agreements enabled access to radar surveys, climate projections, and hydrological models. These arrangements were administrative rather than treaty-based. They depended on institutional relationships rather than legal enforcement. The legal status of buried materials remains unresolved. They are located on Danish territory, placed by U.S. forces, under agreements that assumed permanent ice stability. No court ruling has addressed the matter. Responsibility functions primarily as a negotiated understanding. Over time, legal interpretation shifted from fixed sovereignty questions to adaptive risk management. Agreements written for geopolitical stability are now applied to environmental uncertainty. Their wording remains unchanged. Their application continues to evolve. The Camp Century case illustrates how infrastructure can outlast the political systems that produced it. Documents drafted for defense coordination now influence environmental governance. Their language constrains action without resolving underlying questions. Diplomatic engagement proceeds through gradual consultation, shaped by archives, scientific models, and financial constraints rather than judicial decisions. Paths carved by melt and refreeze. Water moves differently in an ice sheet than it does in soil or rock. It begins at the surface during brief melt periods, spreads across shallow channels, and then disappears into fractures and vertical shafts known as moulins. From there it travels downward until it encounters colder layers or reaches zones where pressure alters its state. In Greenland, this cycle of melt and refreeze has been observed in detail since the early 2000s through satellite imagery, field drilling, and dye tracing experiments. Surface melt on the Greenland ice sheet is not uniform. It varies by elevation, latitude, and seasonal temperature. At Camp Century's location in northwestern Greenland, accumulation historically exceeded melt. Snowfall buried previous layers, preserving stratification. However, observational records from 1990 onward show increasing frequency of surface melt events. The extreme melt year of 2012, when nearly the entire ice sheet surface experienced thaw at some point during summer, provided a reference case for modeling infiltration depth. Hydrologists studying meltwater percolation measure how deeply water can travel before refreezing. In firn, which consists of compacted snow grains with interconnected pore spaces, water may descend several meters. If the firn layer becomes saturated or densified, vertical movement slows. Laboratory experiments conducted at the Geological Survey of Denmark and Greenland simulate these processes by varying temperature gradients and pore sizes. Results indicate that under sustained warming scenarios, meltwater can penetrate deeper before refreezing. Subsurface flow is guided by temperature, density, and internal layering. Ice cores extracted near Camp Century reveal alternating bands of snow deposition and melt features. Each band reflects a seasonal cycle. Chemical analysis of these cores identifies trace substances transported by water. Researchers track ions and isotopes to determine flow paths. These measurements provide indirect insight into how buried materials might migrate over decades. Hydraulic conductivity within ice is generally low, but localized pathways can accelerate movement. Crevasses and refrozen melt channels form preferential routes. Ground-penetrating radar surveys detect some of these features as discontinuities in layering. Over time, Repeated melt cycles can enlarge them. Field observations show that refrozen ice lenses alter internal stress distribution, potentially affecting structural stability. Numerical models integrate these factors to estimate contaminant transport. Inputs include temperature projections, snowfall rates, and chemical solubility data. For Camp Century, researchers used site-specific depth estimates derived from radar surveys. Results vary depending on emission scenarios and accumulation trend. Chemical mobility depends on compound properties. Diesel hydrocarbons degrade slowly in cold environments. PCBs persist and bind to particulates. Laboratory studies indicate that low temperatures reduce reaction rates, but do not eliminate dissolution. If meltwater reaches contaminated zones, it may dissolve small fractions of soluble components. Refreezing can trap these substances in new layers, redistributing them vertically. Field verification remains limited. Direct sampling beneath Camp Century has not been undertaken due to logistical constraints. Instead, researchers compare model predictions with observations from analogous sites. Studies at smaller Arctic installations provide case examples. At certain abandoned radar stations, seasonal melt has exposed shallow waste materials. These exposures inform parameter selection in larger-scale models. Climate projections suggest that northwestern Greenland may experience increasing melt frequency through the mid-21st century. Regional climate models, downscaled from global simulations, estimate changes in accumulation and temperature. Uncertainty remains significant. Variations in atmospheric circulation and precipitation patterns influence outcomes. Monitoring programs therefore emphasize updating projections regularly. Ice dynamics add complexity. The Greenland ice sheet flows outward toward the coast at rates measured in meters per year in some regions. At Camp Century's elevation, flow is slower but continuous. Over decades, horizontal movement can shift buried materials relative to surface coordinates. Models account for this by incorporating velocity fields derived from satellite interferometry. The 2023 Dixon Fjord event provided a separate demonstration of hydrological impact. The landslide-generated tsunami altered local water circulation patterns and redistributed sediment. Although the fjord lies far from Camp Century, the event highlighted how Arctic systems respond to abrupt inputs. Hydrodynamic models developed for that event share computational frameworks with ice hydrology simulations. Researchers also study the role of refreezing in stabilizing contaminants. When meltwater refreezes, it releases latent heat and forms new ice layers. Solutes can become trapped within ice crystals or concentrated in brine channels. Experiments conducted in controlled cold laboratories show that repeated freeze-thaw cycles alter chemical distribution patterns. These findings feed into long-term risk assessments. Monitoring networks include automatic weather stations near historical sites. These stations record air temperature, snow depth, and radiation balance. Data are transmitted via satellite to research centers. Combined with radar surveys, they allow estimation of surface mass balance changes. Trends are analyzed annually and compared with model predictions. Policy discussions rely on these scientific outputs. Environmental agencies request periodic technical briefings summarizing melt trends and transport modeling. The emphasis remains on observation rather than intervention. No large-scale mitigation has been initiated at Camp Century. Decisions are deferred pending clearer projections. Uncertainty does not imply absence of movement. It reflects limits of measurement, resolution, and model assumptions. Hydrological pathways in ice are heterogeneous and evolving. Each melt season contributes incremental change. Accumulated over decades, these increments may alter burial depth and internal structure. Comparative studies from Antarctica provide additional context. There, similar subsurface installations from the mid-20th century exist in colder conditions. Lower melt rates reduce mobility risks. Greenland's comparatively warmer climate places it in a transitional category between polar desert and temperate glacier regimes. Research programs continue to refine parameter values. Ice core drilling campaigns provide updated stratigraphic data. Remote sensing improves detection of melt features. Chemical analysis techniques detect trace concentrations at lower thresholds. Together, these methods narrow uncertainty ranges in transport projections. The buried materials at Camp Century remain encased within a dynamic medium. Melt and refreeze cycles shape that medium gradually. Hydrological modeling describes potential pathways rather than fixed outcomes. Each dataset contributes to a cumulative understanding of how water interacts with ice and embedded structures. Over time, changes in temperature and accumulation will determine whether these pathways expand or remain limited. Current observations suggest incremental alteration rather than abrupt exposure. Continued measurement will adjust these assessments as conditions evolve. Echoes, timed at 92 seconds. In the early hours of mid-September 2023, automated systems at several seismic monitoring centers began registering an unfamiliar pattern. The waveforms arriving from stations in Europe, North America, and parts of Asia did not match the short, irregular bursts normally associated with earthquakes. Instead, they formed long sequences of nearly identical oscillations, each cycle repeated at regular intervals, producing a stable rhythm that continued without interruption. The dominant period measured close to 92 seconds, a value that remained consistent across independent recording networks. Initial classification software flagged the signal as anomalous. It did not fit templates used for tectonic events, volcanic tremor, or anthropogenic activity. Analysts reviewed raw data streams to verify that the pattern was not the result of equipment malfunction or synchronization errors. Clock calibrations were checked against Jeep's references. Instrument diagnostics showed normal operating conditions. The signal was present at stations separated by thousands of kilometers, indicating a geophysical origin rather than a local disturbance. By comparing arrival times and phase relationships, researchers estimated the source location. Triangulation placed the origin in East Greenland, near Dixon Fjord. Satellite imagery from Sentinel-2 and Landsat missions was examined for surface changes in the region. Images acquired after 16 September 2023 revealed a fresh scar on a steep mountainside bordering the fjord. The scar extended several hundred meters vertically and displayed exposed bedrock and disrupted ice. Before and after comparisons indicated that a large mass of material had detached. Volume estimates were derived using digital elevation models and photogrammetric techniques. Analysts calculated that tens of millions of cubic meters of rock and glacial ice entered the fjord in a short period. The sudden displacement of water generated a powerful tsunami within the confined basin. Unlike oceanic tsunamis, which disperse across vast distances, this wave was constrained by steep valley walls and limited outlet channels. Dixon Fjord is characterized by elongated geometry and significant depth variation. Bathymetric surveys conducted during earlier scientific expeditions provided detailed profiles of the fjord floor. These data were integrated into hydrodynamic models. Simulations showed that when the landslide-generated wave reached the fjord walls, it reflected with minimal energy loss. The reflected wave then traveled back toward the opposite end, where it reflected again. This repeated process produced a standing oscillation, known as a seisure. The period of a seisure depends primarily on basin length and average depth. Using measured dimensions, researchers calculated a theoretical oscillation period close to 90 seconds. This matched the observed seismic frequency. Further simulations adjusted friction coefficients and water viscosity parameters to reproduce the gradual decay observed in real data. The modeled energy dissipation rate aligned with the 9-day duration recorded by seismometers. As the water oscillated, it transferred mechanical energy into surrounding rock. Each impact against the fjord walls generated subtle ground motion. These vibrations propagated through bedrock and into the Earth's crust. Sensitive broadband seismometers detected the resulting waves. Because the oscillation frequency was stable, the seismic signal appeared as a narrow spectral peak rather than a broad distribution. Spectral analysis was central to interpretation. Researchers applied Fourier transforms and wavelet techniques to isolate dominant frequencies. The 92-second peak remained prominent even after filtering for background noise. Wind, ocean swell, and human activity typically produce more variable signatures. Their removal left the fjord-generated signal intact. Field observations provided supporting evidence. The Ella O research station, located within the fjord system, reported damage to equipment and structures consistent with a large wave. Debris and sediment were deposited above normal shoreline levels. Vegetation lines on adjacent slopes marked the maximum run-up height. These physical indicators matched modeled wave amplitudes. Global cooperation facilitated rapid analysis. Data from networks such as the International Federation of Digital Seismograph Networks were shared among institutions. Researchers in Denmark, the United States, the United Kingdom, and Germany compared processing methods and results. Independent teams reached similar conclusions regarding source location and mechanism. The persistence of the oscillation distinguished this event from most known tsunamis. In open marine environments, wave energy disperses laterally and vertically, reducing amplitude quickly. Dixon Fjord's confinement limited this dispersion. Its steep walls and closed geometry allowed energy to remain concentrated. Only gradual frictional losses and minor leakage through connecting waterways reduced motion over time. The event was documented in a peer-reviewed study published in Science in December 2023. The authors described it as a rockslide-generated tsunami that rang the Earth for 9 days. The wording reflected the continuous, bell-like quality of the seismic trace. The paper emphasized methodological integration, combining satellite analysis, hydrodynamic modeling, and seismic interpretation. Historical records contain few comparable examples. Some Norwegian fjords have experienced landslide-induced waves, notably the 1934 Tafjord disaster. However, sustained global seismic detection was not possible at that time. Modern instrumentation allowed the Greenland event to be recorded in unprecedented detail. Following the initial analysis, monitoring continued. Subsequent satellite images showed no major secondary slope failures at the same site. Seismic records from later months did not display similar narrowband signals. The September 2023 event remained isolated within available datasets. The resonance observed in Dixon Fjord illustrates how local topography governs energy retention. A specific combination of basin length, depth, and boundary conditions produced a measurable global effect. Without this configuration, the landslide might have generated only a short-lived regional disturbance. The archived datasets now include synchronized waveform files, processed spectra, and model outputs. Each is associated with precise timestamps and geospatial coordinates. Together, they form a detailed record of how gravitational collapse, water motion, and solid Earth response interacted over a defined interval. The 92-second cycle persists in these archives as a numerical signature rather than a visual image. It represents a sequence of oscillations linked to a single fjord on a single date. Its interpretation rests on calibrated sensors and reproducible analysis rather than direct observation. If you found this video interesting, make sure to subscribe and turn on notifications so you don't miss what's coming next. Drop your thoughts in the comments below. Thanks for watching, and we'll see you in the next one.